everyone doing?
Great.
Glad to hear. Anyone need anything or have any questions before we get started? Yes.
Where can you find your lab averages?
Those are not currently publicly posted. I've been trying to mess around with the Brightspace gradebook. It just doesn't want to work the way I want it to. So, as of right this second, I have them all recorded, and the best way to find them is just to ask me. I'm still trying to get them posted,
So like at the end of class we can like just go on to you and ask for it. Okay.
Yeah. Yeah, your grades are not a secret. The only reason they are not like displayed anywhere for you to see is just that I haven't gotten the system for that working properly. It keeps not behaving the way I want it to. But they're not a secret. Please ask. I will tell you them. You should be able to know your grades. I have too many tabs open.
November something. I think which
Better. Anything else in your minds before we get started? All right. We've been talking about momentum and collisions in Chapter 6. Last time, we looked at some more collision type questions, noting again that momentum is conserved in collision. We also further began defining and using the term of impulse in our math, impulse just being a fancy way of saying change in momentum. To start with today, before we learn anything new, I'm going to give you guys a quick example, and I'm going to let you guys sit with it for a sec, see what you come up with. Here we are going to look at the specific collision between a baseball and a baseball bat. We have a 145-gram baseball being launched directly towards Babe Ruth. The fastball is thrown with a speed of 44.7 meters per second in one direction. Babe Ruth is going to hit the ball and blast it backwards at a different speed in the opposite direction. And I would like you guys to tell me what is the impulse of the baseball and how much force is applied to the ball if the collision lasts 0.71 milliseconds. You guys a minute to work on it yourselves or with your classmates, and then we will move on. Any thoughts or answers yet? Bless you. In our quest for the impulse of this baseball, there's many different versions of impulse that we can pursue here. But its definition is change in momentum. And since we know the ball's initial and final velocities, we can figure out its change in momentum. In order to do that, I like mass times change in velocity. What mass should we use?
145.
No, 0.145.
0.145, very good, because the original number is grams and we like kilograms in our formulas. The other thing that we need to make sure to do is that we are correctly orienting our change in velocity. The ball is initially moving 44.7 meters per second forwards before the impact, and afterwards it is moving at 69.4 meters per second backwards. So the change in velocity is not just 69.4 minus 44.7, because that would imply that these two speeds point in the same direction, because they don't. The ball is turning around, which is a much bigger impulse. It takes more effort to knock something backwards than it does to just change its speed moving in the same direction. So delta V, final minus initial, if our final is 69.4 and our initial is 44.7, we have to indicate that these are pointing in opposite directions somehow. Namely, one of the two numbers needs to be negative. You can choose for the second direction to be negative, which would be negative 69.4 minus 44.7. Alternatively, you could decide that the first direction, bless you, is negative. So this is one way to do it. The other way would be deciding the initial velocity vector should be the negative one, which would be then subtracting the negative. Either way, the numbers somehow need to end up adding together because the direction changes. We have to lose all of this before gaining this in the opposite direction. So the magnitude of the change in velocity, whether positive or negative, needs to be 114, not 25. Yes?
So like for the change in momentum, do you always just use the change in velocity, or do you ever use like the change in mass? Because it's just like saying the change in momentum in general.
The only reason I don't use the reason that I don't usually write out delta M times V is that it's a very rare scenario.
Okay.
Because an object's mass never just spontaneously changes. If you think about it, the only reason an object's mass should change is if you are adding material to it or taking material away, in which case you could instead consider them as just separate objects. And if one object like breaks into multiple pieces, yeah, its mass went down, but now it's more than one object. So that's, the scenario where M changes is rarer and weirder. And so I tend to generalize it just as this, one object with a changing velocity. Does that make sense?
Yeah, so
Okay.
just disregard mass change, their abilities.
Yeah, it's like, it's possible, like, there are ways, like if you had like a moving train and while it's moving, a bunch of stuff got dumped into one of its cars, you could kind of consider that a mass increase, but its speed would also change. So mass changing is a weirder scenario. Does that answer the question? Okay. It's possible, it is possible, but here the mass of the baseball stays constant and the velocity changes. And as long as you make these two velocities point in opposite directions somehow, you should get a very big change in velocity. And how much should the ball's impulse be?
16.54.
Very good, 16.54 approximately. What is the unit for impulse and momentum?
Kilograms times meters per second.
Very good. And once we have that, we can use one of the other impulse formulas to figure out the force that was applied to the ball. So take that 16.45, that's going to equal the force of the bat times the time that the bat was touching the ball. We're not going to plug in 0.71 because that's in milliseconds. How many seconds do we plug in?
0.00071.
Correct. And that should give us a very big number, actually. Yeah, that's the right number of zeros. $97,000 newtons, which is a scary number. Again, for context, that's about 97 times what I weigh. Baseball bats are dangerous. Note again, though, this is the force that the bat hits something with. This was not Babe Ruth's punching force. He was using a tool to generate torque.
Why isn't the impulse negative?
Well, whether or not it's negative just kind of depends on whether you think the initial direction or the final direction is the negative direction. It could be negative. If we define the first as forward and then the second as backward, then it would turn out negative. It looked like this. You get a negative impulse and therefore a negative force. I didn't necessarily state which one had to be positive or negative. You just have to make sure they have opposite signs somehow. Hypothetically, if you define the after direction as forward, you can get positive answers and still be right. Lots of hands. I think yours was next.
I keep getting like 23,000.
Yeah.
Same.
Oh, 23?
That's what I got.
That's what I
Yeah.
got.
Did I do something wrong?
I think it's 3.
Oh, you know what it is. Teachers make mistakes, please call me out on them. I transposed the 1 and the 7 when I was typing into my calculator. I divided by 17 milliseconds. That's my bad. Thank you for pointing that out. So, if I fix that, thank you. That 97 did not make much sense. The actual number should be, as you all said, 23,302 and some change. That makes way more sense. Thank you. Please call me out on my mistakes, because I don't want to propagate my own error. Yeah, if you got this, you're right. I typed the wrong thing into my calculator. Thank you all.
Do you still want us to so you want us to round it to that 300?
Oh.
Because it's 23.
Oh, I forgot the 2.
295.
I forgot the 2. That's another mistake. I'm having an off morning. Thank you.
23,295.
Yeah, 295.
That's what I got.
Bro.
Oh, I got 23,302.11.
No.
That's what I got, but I didn't.
I got the 295.
All right, the variances might, okay, yeah. I wrote this, but I actually carried what my calculator gave me through, so it's a few more digits. This is why when I'm grading on tests, rounding doesn't bother me. Like if you just said 300, I'd take that, because the answer you get depends on your rounding sometimes. So, apologies. Again, I'm apparently having an off morning. Please call me out on these things. What's on the board, interpreted literally, would give, that's 295.77 instead of 302.11. So, either's fine. They both round to approximately the 300 anyway. Apologies again. So, about 23 times what I weigh, which is again still dangerous. Pretty much the entire point of all tools is to generate torque and increase the force output. Turns out, all of sports is applied physics. If you're using a bat, a racket, a golf club, etc., you are just weaponizing torque. Which is actually what we'll talk about next week or week after next. Questions here? All right. Now, we've been discussing how in collisions, momentum is always conserved. Momentum is always conserved in collisions, and technically, this is like how energy is always conserved in any interaction, because no matter what you do, the total amount of energy before and after an action still exists, even if it's in a new, different, weird, hard to measure form. But momentum is nice because it's always momentum. It's usually easy to track because it only has the one form it can occupy. But in every single collision that involves momentum, kinetic energy also has to be involved by virtue of the fact that if you have momentum, you also have kinetic energy. Both require mass and velocity. An object must be moving, meaning you can take the same MV, take an object at its current velocity, put them into the two different formulas, and that will indicate that the object simultaneously has both momentum and kinetic energy. And so far we've only been looking at really what happens to momentum in a collision, again because it's easier to track. It only has one form that it can occupy. But whenever there's momentum, there's also kinetic energy, meaning that every single collision not only has momentum in it that is conserved from start to finish, all collisions also involve kinetic energy. And similar to momentum, the amount of energy that exists before a collision must be the same as the total amount of energy that exists afterwards. It's just whether or not that energy is going to remain in the kinetic form. Bless you. All collisions, no matter what type, no matter what two things are colliding, momentum will always be conserved, but simultaneously, there's going to be some amount of kinetic energy being exchanged along with the momentum, and whether or not the kinetic energy is specifically conserved within the kinetic state is going to depend. We know that the total amount of energy present will be conserved. It's just a question or not of whether it stays in the kinetic form. Because we've already looked at energy transformations. We know that energy can turn into lots of different states. But exactly what it turns into kind of depends on what type of collision you have. And there are two primary collision types. Those being elastic collisions, wherein elastic objects collide and they tend to bounce off of each other, or inelastic collisions, where the objects don't bounce off of each other. In fact, they tend to stick together after such a collision takes place. And having worked a few momentum collision examples, we are now going to try to classify collisions as one type or the other, and try to analyze what happens to the kinetic energy in those collisions in addition to the momentum in those collisions. How do you guys feel so far? Okay. Now, to kind of illustrate what's happening to the kinetic energy in a collision, I actually want to go back to one we've already worked. This is the first collision example we did, launching an arrow at a wooden log. So our initial state, arrow is flying forward at 25 meters per second. Mass of 10 grams, excuse me. Being launched at a log. Log's initial velocity is 0. And its mass is 25 kilograms. After the arrow collides with the log, it just kind of embeds itself within the log. The objects stick together. And as a result, we figured out the speed that they will move at after the crash once combined like this. From your notes, do you guys have that velocity?
You mean 5 kilograms for the log?
Whoops, yep, sorry. I am really having an off morning, aren't I? 5 kilogram log, apologies.
0.05.
Thank
That's
you.
what I have.
So using conservation of momentum, we determined that the final speed of the log and arrow combined after impact should be 0.05 meters per second. We remember this? Okay. We got that conclusion by looking at the conservation of momentum specifically. I want us to now look at what happened to the kinetic energy in this scenario, because since energy in general is also conserved regardless of what type of interaction you have, we can track kinetic energy through this akin to how we can track momentum. The only exception is that kinetic energy is not always conserved in the kinetic state, like how momentum is always conserved as momentum. So what we did last time was this. But right now, I want us to double back and look at this. Look at the total kinetic energy on each side instead, and see if they're equal to each other. Does this premise sound all right so far? But right now we're just seeing if the kinetic energy is conserved, and that will help us determine what type of collision this was. Initially, across our two objects, which one of these two things would have kinetic energy?
The arrow.
The arrow. The arrow is the one that's moving. So the kinetic energy of the arrow would be 1/2 times its mass times its starting velocity. The log doesn't have any kinetic energy to start with because it's not moving, like how it didn't have any momentum to start with the last time. So initially, the arrow's got all the kinetic energy. So this is just the kinetic energy of the arrow. Arrow's mass, arrow's initial velocity. We're going to compare that to the amount of kinetic energy that would exist in the system after they collide. And after they have collided, their combined mass is now moving at this speed. We could treat them as one united object. I'm going to list them as two objects, at least here at the start. So the sum of all the kinetic energies after the crash, we'd have the kinetic energy of the arrow after it's slowed down to our new final speed. So this is the arrow's final kinetic energy. And we're going to add to that the log's final kinetic energy. So that's the sum of the kinetic energies of both objects afterwards, since they are now both moving. The log's initial KE is 0 because its initial velocity is 0, but afterwards they both have some non-zero velocity. And so we're just going to figure out how much kinetic energy remains after the crash. Feel okay so far? All right. On the initial side, 1/2 times 0.01 times 25 squared. The arrow began this process with approximately 3.125 joules of kinetic energy. So that's the initial total. That's all the energy the arrow had, and the log didn't have any. So this is, our initial total is just the initial KE of the arrow. On the after side, we can find the final KE of both the arrow and the log. The arrow's final kinetic energy is a point 0.0000125 joules of kinetic energy remain in the arrow. And the log, with its much larger mass at the same speed, has 0.03125 joules of kinetic energy remaining. If we add those two numbers up to determine the final amount of kinetic energy in the entire scenario, our final kinetic energy total is 0.03125 joules. Are those two sides equal to each other?
No.
No. And there's no trick to make them equal to each other. They're just not equal. That's why I've been putting a question mark over the equal sign. The two sides here are not equal. This means that a bunch of energy, like most of it, is no longer kinetic energy anymore. We had this much KE, and now there's only this much left. Like 99% of it is seemingly gone. And this is because kinetic energy is not always conserved in a collision, unlike how momentum is. The fact that kinetic energy was very not conserved here tells us that this was an inelastic collision. This is the definition of an inelastic collision. The kinetic energy was not conserved. Yes?
So in an elastic collision, they would be equal to each other?
Correct. For a perfectly elastic collision, the two sides, the kinetic energy initial, would equal the kinetic energy final, like how it does with momentum.
In the second part, where is that 25? What is that from?
Sorry, say again?
The 1/2 times 25 times 0.05.
Oh, this?
The 25.
That is the, I did it again.
Sorry.
That's supposed to be the mass of the log, and I wrote 25 instead of 5.
It's okay.
I am so sorry. This might be my most off day of the semester. That changes our answer slightly. Thank you for calling me out on that. That actually makes the energy conservation even worse. We stored even less energy in this collision. Most of that kinetic energy is gone, even more than I originally thought. Thank you again. Apologies. And this happens again in an inelastic collision. So now that we've looked at the kinetic energy, the big thing to write next to this in your notes is that this type of scenario is a textbook inelastic collision. I'm always very specific when I'm saying the in part because I always feel like I'm always hyper conscious about saying the inelastic part to make sure it's clear I'm not saying an elastic collision. So this was an inelastic collision, not elastic. Textbook type of inelastic collision. The two objects physically stuck together, nothing bounced off of anything, and as a result, most of the kinetic energy is gone. Now, was that energy destroyed? No, because energy can't be destroyed. The missing 3.06 joules of kinetic energy is just somewhere else in a different form. Probably heat because of friction. In this specific scenario, the log would act on the arrow with a frictional force as the arrow embeds itself in the log. The log would exert a force on the arrow as the arrow embedded itself a distance in. That force times distance would tell you the work that the friction from the log did on the arrow, and that just took energy away from the arrow while only transferring a teeny bit into the log itself in the kinetic state. That work turned most of it directly into friction, and that slowed the arrow down and just kind of made the energy useless heat that we can't see anymore. Again, this is a textbook what happens in any type of an inelastic collision. The primary features of inelastic collisions are that the two objects involved in the collision stick together, and overall the collision tends to be very sluggish as a result. Everything slows down, energy's not conserved. It's literally very unenergetic. Other common examples of inelastic collisions like this would include most things hitting the ground. Unless it bounces off of the ground, that's probably an inelastic collision. I watched too much Looney Tunes as a kid, so I pretty commonly bring up just an anvil making a crater. That's inelastic. They don't bounce away from each other, it just made a crater and everything stopped. But a more common, less silly example of an inelastic collision is actually car crashes. Car crashes are by design inelastic so that all the energy involved in the crash is just absorbed, and so that everything is slower after the fact. You don't want car crashes to be elastic, because if you keep all that kinetic energy, the two cars are likely just going to spring off of each other and launch you into traffic and give you really bad whiplash. So for that reason, inelastic collisions tend to be more common, if boring, but boring is safe, unfortunately. And this is different to elastic collisions, where the energy is conserved, bless you, alongside the kinetic energy, alongside the momentum, excuse me. Now in lab this week, if you've already had lab, you know this, part of the lab was investigating the difference between the two. If you haven't had lab this week, again, bring the notes. I now want to at least begin examining an elastic collision. And I'm going to kind of ramp this up to the extreme to demonstrate why you don't want car crashes to be elastic. Sure, it's a pain to have to fix your bumper after every fender bender, but trust me, making the bumper out of rubber to stop that problem means you're just going to end up worse off in the end. So we're at least going to start this example. We might not finish it today, and that's fine. We're going to start examining a hypothetical car crash. We're going to make it an elastic collision. Say these cars just have super rubber bouncy bumpers on them. Again, to demonstrate an extreme example of why you don't want that. So here we have two cars pulled out of fiction. the smaller sports car from Knight Rider, called Kit, and the much bigger villainous truck from Transformers. It had to be a bad guy. Optimus Prime's evil twin is Nemesis Prime. So here, two talking cars are going to square off and just collide straight on into each other. And we're going to treat this like an elastic collision. So, two cars of a very different mass approaching each other at equal but opposite velocities, 40 meters per second respectively. They both have very different masses. The sports car is 400 kilograms, and the semi-truck is 2,000 kilograms. Who do you think is winning this fight, relatively speaking? The truck, very good. I'm not saying, the recommendation is always don't be involved in a car crash, but usually the one with the bigger mass tends to win the encounter, because bigger mass means you're less likely to change velocity, and you don't want to change velocity. That's what gives you whiplash.
Isn't the velocity 45 meters per second?
That's like the fifth time I did something wrong today. Thank you again. I need you guys to call me out on this stuff. Now, realistically, if this was an inelastic crash, most cars are designed to have inelastic collisions. The bumpers are made out of non-elastic materials, mostly metal. Sometimes there's some styrofoam padding in there. Designed so that when they crunch in the crash, they stay crunched. Again, if you've ever been involved in a fender bender, your bumper probably got dented. It's kind of a pain to have to deal with, but trust me, you want it to dent, because if that dented, it means that there was a lot of energy, a lot of work spent in denting the bumper, and now that energy isn't kinetic anymore. If the bumpers were made out of something like rubber, elastic objects that are able to spring back to their normal shape upon being deformed. Again, if you remember how EPE works, objects that can go back to normal, elastic objects, store the energy and then release it afterwards. That means that once the bumper compresses, rather than staying compressed, it's going to go back to normal and release all the energy it absorbed. And so rather than the two vehicles just kind of stopping, they're going to ricochet off from each other as their rubber bumpers would, in this weird hypothetical case, go back to their normal size. And in all probability, it's going to cause one of these two to rocket away at extreme speeds. This is again why real cars have crunchable bumpers that do not return to their normal shape on their own. You want your car to have bumpers that collapse and a crumple zone, if you've heard that term before. If you want the car to crumple so that you don't spring off into traffic and so that your neck doesn't have a really bad day. So after this very weird elastic car crash, these two things are likely going to bounce away from each other at different unknown final velocities. And we got to figure out what those final speeds are. We want to know the speeds that each vehicle will be going at so that we can figure out, how bad this situation would be. So we're just going to set this one up and we'll finish it on Friday, because frustratingly this one's going to take a few bits of algebra. As with all collisions, we can study this through the lens of conservation of momentum. Total momentum initial should equal total momentum final. Initially, both vehicles actually have momentum this time around, but it's worth noting that they are moving in opposite directions. But they do both have initial momentum, so momentum car initial plus momentum truck initial. And this should be equal to the sum of their finals as well after their velocities change. From the car's perspective, we've got its mass of 400 kilograms and its initial velocity of 45 meters per second. Pointed, I'm just going to call that forward. Meanwhile, the truck has 5 times the mass and is moving at the same velocity but in the opposite direction. Momentum is a vector, velocity is a vector. We care about the direction sign for this reason. This does actually mean that the total momentum of the entire left side here is actually going to end up being a negative number. The negative, though, just meaning left. That means the total momentum of this entire system points leftward, which, again, is very bad for the sports car. So if you get a big old negative number on the left side here, that is okay, that is by design. There is technically negative momentum here, but that just means leftward pointing momentum. I'm gonna go ahead and total up the left side just to show what I mean. 400 times 45 is 18,000. Meanwhile, the truck has 5 times that amount in the opposite direction. So that's negative 90,000 units of momentum. And again, the net momentum of the entire system is going to be negative, pointing to the left. That's because same speed, but the truck is moving, has more mass. So overall, the net momentum of the system is leftward. Again, that is very bad for the sports car. This would be
Negative 72,000.
Thank you. So that's the left side completely summarized. That's the total momentum in the system, and that number would have to remain constant all the way through. Now let's look at the final side. The masses of the two vehicles are going to remain unchanged. The problem is that we don't know either of their final velocities yet. We don't know the speed either of them is going to ricochet away at. Yes?
Would they be going at the same final velocity?
That is not guaranteed. Given that elastic collisions are very chaotic and that the objects don't tend to stick together, you can't guarantee that. We don't know for certain what speed or even what direction these things are going to be moving in. Because elastic collisions uniquely, things tend to turn around and bounce away in the direction they came from. I've been throwing this golf ball all week. Noise incoming. Elastic collision. It bounced away, changed direction. So we don't officially know what direction anything's moving in. We don't officially know the final speed of either of these vehicles. We cannot assume that they're the same, like how in an inelastic collision, the objects tend to stick together at a shared, united final velocity. That means we have two unknowns. Guess what comes next? Algebra and also 2 equations for our 2 unknowns. We need a second equation. Again, we're setting it up for the day. We're going to do all the algebra lines next time. Don't worry, I'm not going to keep you late. What I'm going to point out is that while it is frustrating that we have to consult the second equation, we have a few choices in second equations to consult. So these are your new formulas in addition to conservation of momentum. Since this is an elastic collision, the total kinetic energies, initial versus final, will also be the same as each other. So this, for an elastic collision, is a second starting point that we can use as a second equation with the same two unknowns in it. And so what I'd recommend in that case is basically the same as we did here. We would do the same thing elsewhere on our work page. I would probably do it over there. And compare the total and final kinetic energies to each other. We did that a second ago looking at the arrow hitting the log. In that case, the totals didn't equal each other because that was an inelastic collision. But if we're treating this as an elastic collision, just to see what happens, then the two sides here would be the same, and we can use this as a second equation with the same two unknowns in it. Because if we filled this all the way out, it would have to have all the same unknowns in it. The momentum and kinetic energy formulas both have m and v in them, and no other unknowns. The only complications with the kinetic energy formula is the 1/2 and the squared. But it's still the same unknowns. So we could fill in all the same pertinent details, get a second equation with the same two unknown velocities in it. And that's what we're going to demonstrate next time. So mark your place in your notes. We'll resume this one on Friday. And close out chapter 6. Questions? Let me know if you need anything. Come to the lab as normal, bring your notes. Have a wonderful day. Hi. Yeah. Nice to meet you.